Okay, so welcome everyone. This is the CAR-T Symposium, Breakout Session D. The topic is heavy duty and non-road transportation emissions. My name is Haobing Liu. I'm an assistant professor in the Department of Civil Construction and Environmental Engineering at the University of New Mexico. I serve as the moderator of this event. The session will last about 1 hour. With 3 great presentations from both industry and academia. So each of the presenters will be given about 16 minutes for the presentation. I will give you a reminder within the last 2 minutes. And during or right after the presentation, the audience can use the Q&A function in the platform to ask questions. And depending on the schedule, we will have probably 2 to 4 minutes discussion after each presentation for any questions. I do want to say I really appreciate if you can just use the Q&A function instead of chat box to ask questions so that the presenters and me can have all the questions in the same window so that we don't miss any questions. Okay, so with that, let's get on to the topic. Our first presenter is Phil Lewis. So Dr. Lewis is an associate professor and associate department head in the Department of Construction Science at Texas A&M University. And he is also associate research engineer with Texas A&M Transportation Institute. His research specialty area is economic, energy, and environmental impacts of non-road construction equipment. Dr. Lewis, whenever you're ready.
Haobing, can you hear me?
Yes, I can hear you now. I can hear you now.
I can't hear you.
But you okay.
Let's go ahead and move on to the next presenter while Phil works out his technical issues, and then we'll circle back to Phil after next presenter.
Okay.
I can hear you, Jill, but I can't hear Haobing.
Okay. Well, we can hear you, so why don't you just go ahead and present?
Yeah. Why don't we just get started? Yeah.
Yeah. That sounds good.
Okay. Okay.
Yeah.
Okay. Hi, everyone. My name is Phil Lewis. I'm an associate professor with Texas A&M, and my co-investigators on this project are Adam Mayer and Jeremy Johnson, both with the Texas A&M Transportation Institute. I'll be talking today about some heavy equipment, indoor air quality, specifically what goes on inside the cabs of those equipment. Most anyone who's ever been around that type of equipment, and especially inside the cab, they'll know that it gets very hot and very dirty in there. But to the best of our knowledge, no one's ever really conducted any types of studies, especially an indoor air quality type of study, to find out or characterize what really is going on in there. So the cab air quality is really a function of 3 different environments. There's the climate, the outdoor climate. There's the job site itself, so what kind of project is working on. And then there may be other sources such as smoking or eating inside the cab and things like that. One other thing is that there are really no permissible exposure limits for diesel exhaust specifically. And so we don't really have a very good benchmark to compare our findings to. So anyway, those are some of the things we were looking at here with this study. So what we did is we wanted to focus on some of the pollutants that we did have the equipment to collect the data for, but also some that are contributing to human health. So the data we wanted to collect for the pollutants we wanted to collect were carbon monoxide, carbon dioxide, nitrogen oxide, nitrogen dioxide, particulate matter, PM 2.5, and also black carbon. So what we did is we took our instrumentation and put it inside the cab of the equipment. So for the gaseous pollutants, the CO, CO2, and NO and NO2, we used the MX6 hybrid instrument. We also used the personal data RAM PDR 1000 for PM 2.5, and then we used the MicroF AE51 for black carbon. And here are some of the technical specs on the instrumentation if you're interested. So what we did is we did do multiple tests for different types of equipment that were operating on job sites in the College Station area. We collected data from the cabs of 2 bulldozers, 3 excavators, 1 rolling compactor, 1 rotary mixer, 1 tractor, and then 1 wheel loader. So here are these next few slides. I won't go through these line by line, of course, but these are the results that we collected, just the maximum and the mean values. So for CO and CO2. Here are the values for NO and NO2. And then the values for black carbon and PM 2.5. So with benchmarks, so what do we compare it to? So the way we treated this was we sort of evaluated the equipment cab as an indoor environment, because most of these cabs are enclosed. And in fact, all of the equipment that we tested had enclosed cabs. So we just looked and tried to find some standard IAQ measurements to use as comparison. And these came from different areas. Some even came from the Canadian Health Organization. But so the benchmarks we were comparing to were for CO 11 parts per million, CO2 1,000 ppm, NO was 25 parts per million, NO2 1 to 5 ppm, and PM 2.5 0.1 milligrams per cubic meter in the short term, and PM 2.5 0.04 milligrams per cubic meter in the long term. So for CO, in the 24 tests that we conducted, so out of all that equipment, we came up with 24 tests. Out of those 24 tests, in 19 of those, we were able to detect some level of CO. So the maximum concentrations range from 4 to 15 parts per million, and that was the highest level that registered. And then the mean values, however, they did not approach that exposure limit of 11 parts per million. So we did have 5 tests that had maximum concentrations greater than that. So it could be somewhat inferred that if the maximum level exceeds 11 parts per million, then it theoretically could get high enough that you'd have an average or a mean value higher than 11 parts per million. And so anyway, CO is a pollutant for equipment cabs that could potentially become a health issue. For CO2, here we had ambient concentrations of CO2 was around 300 parts per million. For purposes of our study and based on some of the literature we saw, elevated levels of CO2 greater than 1,000 parts per million indicates poor ventilation and could lead to human discomfort. Could also lead to distraction of the equipment operator, which is something that you don't really want on a construction site. So in these tests, 3 out of the 24 tests had an average of CO2 greater than 1,000 parts per million. And then we had 11 tests had maximum values greater than 1,000 parts per million. And so ventilation in equipment cabs may be generally unacceptable regarding indoor air quality, especially if you're using the standards that are commonly used in buildings. For NO, the diesel exhaust infiltration is the most likely source of NO in equipment cabs. 15 of the 24 tests recorded the presence of NO, and with a maximum concentration ranging from 1 to 28 parts per million. However, none of the mean values approached that long-term exposure limit of 25 parts per million, although we did have 2 tests that had maximum values greater than that at 28 ppm. So again, just like with CO, it may be possible in equipment cabs to achieve sustained levels of NO that could exceed those long-term exposure limits. For NO2, again, the most likely source of NO2 concentrations in the cab is going to come from the diesel exhaust from the tailpipe. 5 of the 24 tests detected any level of NO2. So if you go back and look at the slide with the NO2 data on it, you'll see we registered a lot of zeros. So we only had 5 tests that detected any level of NO2. The maximum values range from 0.2 to 0.4 parts per million, which are well below the published long-term and short-term exposure limits. And then approximately 80% of the tests did not detect any level of NO2 at all in the equipment cabs. PM 2.5, we had 13 of 19 tests that successfully acquired data. We had some tests that with our PM instrumentation that didn't register. So we only had 19 tests for PM 2.5, but out of those 13, sustained mean values over the 8-hour period greater than the acceptable long-term exposure range. So I didn't mention this in the methodology, but to just clarify, the way we did these tests is we took our instrumentation and put it in the cab first thing in the morning before the equipment operators got there and started work. Just left it in there all day. Then when they were finished working, we would go back and take it out. So we were just really trying to get an idea, an initial indication of what was going on with respect to air quality inside of those cabs. So there were, obviously many more things we can do in future studies. But for now, we were just trying to get that initial indication. So these tests were typically done over about 8 hours. And so here again for PM 2.5, all but 2 of the tests had maximum values that were greater than the acceptable short-term exposure range, values up to 17 milligrams per cubic meter. And then, although it's not possible to distinguish diesel exhaust particulates from dust or these other particles, the results that we achieved do indicate that PM 2.5 has potential to have both short-term and long-term health effects for equipment operators. With black carbon, we considered that to be a constituent of PM 2.5. So the BC concentrations were lower than those overall PM 2.5 numbers we got. So even though there are no published exposure limits for black carbon, what was significant here was that we had 5 tests with maximum values that equaled or exceeded the 0.1 milligram per cubic meter short-term exposure limit. We also had 10 tests that had maximum values that equaled or exceeded the 0.04 milligrams per cubic meter long-term exposure limit. So accordingly, black carbon has high potential to be a health hazard for diesel equipment operators. So here are our main conclusions. Since CO was present in the cabs for most of the test, and in some cases we had maximum values that exceeded the recommended concentrations, we considered CO to be a potential health, safety, and productivity hazard for equipment operators. CO2, that's primarily a comfort issue for the equipment operator. We didn't see any levels get high enough for it to be really a health concern. But again, once it got over 1,000 parts per million, it does become more of a ventilation issue, a thermal comfort issue for the operator. And so it may serve as a distraction that could reduce productivity and possibly pose a safety threat to others working on the job site. So that has potential to be a health hazard for equipment operators. However, NO2 rarely appeared in the results and does not likely pose much of a threat as NO. And then probably the greatest potential as a health threat is PM 2.5 and black carbon. And again, some of that's coming from the diesel exhaust. Most of it is likely coming from the job site itself because these can be very dry and dusty environments. So inside that cab, the main concerns that we came away with were CO as far as gaseous pollutants, and then particle pollution in the form of PM 2.5 and black carbon. So anyway, the limitations and recommendations on our study, we sort of took the approach here that something is better than nothing. And that was just our initial study. So we do have a new project being funded by CAR-T that we're working on now, where we are testing more equipment and collecting more data. We are trying to characterize the equipment and the activities that it is during doing the test, and we're also trying to characterize the operator behavior during the test itself. So anyway, I think I'm drawing very close to the end of my time, so I'll take a few questions here.
Thank you, Doug Lewis. Can you still hear me? Maybe not. Rainbow asks, are you still there?
I can hear you.
Yeah. Do you mind read questions for Phil, because he
yeah,
cannot
Jill,
hear
I'm
me.
not sure why I can't hear him.
Yes. Let's see.
From Dr. Mary Fox. Yeah.
She said, important work. Did you look at combinations, i.e., did high values occur for multiple pollutants in any particular type of equipment?
We didn't really notice any different. Well, okay, yeah. So some of the equipment did have higher levels than others, especially the rotary mixer, because that is a stationary piece of equipment. And if you've ever seen one of these things operate, you just dump stuff into it and it either grinds it or mixes it up. So you get a lot of dust coming out from that. So yeah, the PM concentrations were really high around that rotary mixer. As far as the mobile equipment, we didn't see one thing that just really stood out compared to the others. And again, we fully believe that's more related to the job site and the activity that the equipment is performing rather than the equipment itself.
Great. Would you like me to read any other questions?
Yeah, from Victoria.
Yeah, if we have time, that's fine. Yeah.
Why CO2 from Victoria?
I think the question is why do you test CO2 concentration, maybe?
If I'm totally honest about it, we collected it because we had the instrumentation and it just collected the data anyway. So we did compare it, but no, we don't really consider CO2 to be much of a health issue. Now, in a previous study, when we collected CO2, what we did see there is that thermal comfort. So in other words, we calculated the heat index inside of the cabs, and even sometimes in the cooler winter months, we saw some heat indexes get up into extreme levels. Now, of course, they're probably running the heat in there as well, but coupled with the CO2 measurements we got, we saw that there were some fairly high heat indices in those studies inside those cabs, even when the outside temperature was much cooler.
Okay, next from Kevin.
Thank you, Phil. We're going to move on to the next presenter. Thank you.
Okay, thanks. Sorry for the technical issues, but yeah, thanks a lot.
Can other presenters hear me? Chaz, can you hear me?
Mm-hmm. Yes.
Okay.
I can.
Okay, thanks. Let's move to next. Our next presenter is Chaz Frederickson. So Chaz is a PhD student at UC Riverside in mechanical engineering, and his research has been focusing on the marine and off-road emissions and activity. He currently had 3 years of experience researching at Center for Environmental Research and Technology at UC Riverside. Chaz, you can take it away.
All right. And you can hear me just fine? Just making sure?
Yes.
Good, good. Okay. Hello, everyone. My name is Chaz Frederickson. Today I'll be talking about the project of measurement of gaseous emissions from commercial hovercraft during real-world operations. Before I begin, I would like to thank the people at CARB and MTU that helped make this project possible. All right, so the project overview. We were trying to evaluate the gaseous emissions for commercial hovercraft with EPA Marine Tier 2 and Tier 3 engines in-use operations using portable emission measurement systems. And just a little background, back in 2017, CARB introduced a regulation that would require new marine engine purchases to be EPA Tier 2 or higher. This regulation is based on a schedule with deadlines all the way through 2022. And by the end of this, all CHC, commercial hovercraft, would be required to meet EPA Tier 2 and Tier 3 standards. So the main hope for this regulation would be that emissions would be reduced through turnover of new engines, turnover of old engines and older vessels. All right. So our test vessels for this project, we were using 2 high-speed ferries. The first vessel is a EPA Tier 2 vessel with a capacity of 450 passengers. It was equipped with a water muffler, and when we were testing on it, it operated on 3 out of its 4 engines. For vessel 2, it was a Tier 3 engine, and this vessel was a little bit smaller. It had a capacity of 400 passengers, and this one was equipped with a retrofit SCR and DOC after-treatment system. However, after the test, we found out, it was confirmed to us that the SCR system was non-operational and without urea dosing. So when you view the results of this project, please keep that in the back of your mind that the SCR system was not quite working. And below, I provided a table with some information about the 2 engines that we tested on. So for vessel 1, it was a 2009 engine producing 2,000 kilowatts, and this engine had a total runtime of over 18,000 hours. Whereas vessel 2 is a bit newer. It had a 2015 engine producing 1,455 kilowatts and had a total runtime of about 6,400 hours. All right, so moving on to the experimental setup. We used a PM PEMS and a gaseous PEMS. For the PM PEMS, it was the AVL MSS MOVE, which used 2 different measurement systems. The first and main one was the photoacoustic suit measurement, and then it also used a gravimetric mass measurement using a Teflon filter. For the gaseous side, we used a Semtech DS, which used a NDIR analyzer for CO, CO2, and hydrocarbons. It used a ultraviolet analyzer, NDUV, for NOx, and then it also used a heated flame ionization detector for THC. So for the first vessel, the picture on the left, these instruments were located in the engine room of the vessel, and our sample location was just above where this picture was taken. However, we weren't quite just at engine out. There was the water muffler between engine out and our sampling locations. And what this water muffler did was inject seawater into the exhaust to cool it and to reduce noise. We were told that this was done for the comfort of the riders. However, this did inject a large quantity of water into the exhaust, so we had to work around that using a water knockout system. However, even though we used the water knockout system, we were not able to get valid particulate matter results from this vessel. For vessel 2, these 2 These instruments were located in the exhaust stack of the vessel. And since it had the SCR, we wanted to look at engine out and then also the post SCR location. So, so we could see what kind of effect the SCR was having on the emissions. So for this one, we did have engine out, and then the other sample port was actually on the next deck above where these instruments were above the SCR. All right, so took a little look at the vessel activity, which we were able to get. So these plots are showing the amount of time spent the vessel took on each load bin for engine power. So for vessel 1 in the gray bar, this is representing the amount of time that we sampled for the 2 days that we were there sampling. And we, excuse me, have sampled about 15 hours of activity for this one. And then the green, the historical activity, which we were able to download from the engine thanks to the MTU personnel that were there, is based off of the total runtime. So we're talking the 18,000 hours that the engine has on it. For vessel 2, the blue is representing the amount of time that we spent on that one sampling. Again, another 2 days of sampling, and we captured about 20 hours of activity. And then the orange, the historical activity, is the 6,000 hours of the total runtime. So we can kind of see that there is a difference between our measured activity and the historical activity. We can contribute some of these differences to the weather that we had while testing. There might have been some operational changes to the vessel prior to testing, and also the impacts of testing, and also the length of testing. We only measured, less than a whole 24 hours of activity, and that might not be fully representative of the whole historical. What you can also see by these plots is that they take on a bimodal shape, wherein these vessels spend a great deal of time at rather low loads, below 30% engine power, but they also spend a decent amount of chunk of time at pretty high loads, at above 80% load. And it's just an important note that the vessel 1, spent 30% of its time below 5%. So 30% of the time was basically idle. And for vessel 2, this was about 17%. So then moving on to the transient emissions. This is for the first vessel, vessel 1, the tier 2 engine. Here we have the mass rate of all the pollutants that we collected, along with the engine power. And what this shows is that a typical run for this vessel, it was about a half-hour trip one direction. And once leaving the terminal from where this vessel took off from, it would move out past like the no-wake zone where the speed is limited. And then as soon as it got to open water, it would accelerate all the way up to basically 100% load and stay there for the entirety of the trip. So we only really got transient load data when it was accelerating up and then when it was decelerating down to maneuver into the next terminal. Otherwise, it was basically a steady state operation. For vessel 2, we have the post SCR and then also the pre-SCR trips. Again, these are the kind of usual trip that you would see from this vessel. These trips were about an hour long. And as you can see, they take on a pretty similar shape to vessel 1, where they'll kind of have rather low load when they're getting out of an area, and then once they're into the open water, they accelerate to their maximum, to 100% load. One other thing to notice here would be that the NO pollutants, there is a reduction in NO in the post-SCR tests. But if you were to look at the NOx doesn't change very at all. And during testing, this is one of the indicators that we had that our SCR system was not fully functional when we saw this. All right. So next we have the normalized brake specific emissions. Here we have the pollutants plotted in grams per brake horsepower hour. This is for the entire testing period. And you can see that vessel 1 has just a slightly lower gram per brake horsepower hour for CO2. And then it kind of changes for CO, NO, and NO2. Vessel 1 did meet its Tier 2 certification standard for NOx, as did the Vessel 2. Just about is right at the level of a Tier 3 certification level. And then Vessel 2 also did meet its certification level for particulate matter. One other thing I wanted to look at here would be the change between NO and then also NO2 from the pre and the post SCR. Even though the SCR system was not fully operational, it was still on there and still having an effect on the emissions. So for the next slide, we have a comparison for vessel 2 of the NO to NO2 ratio. And as you can see for the first few parts, we have the it put into load bins for pre and post SCR tests. So for the first load bin, less than 5% load for a pre-SCR location, we see that it's largely NO. And then as we go on to the post location, there's a large conversion of NO to NO2. And then as this trend kind of continues, but as load continues to increase, the conversion of NO to NO2 is not quite as great. And I have to say that this was not part of the study. So more research would definitely have to be needed to investigate this more thoroughly to see what kind of effect the SCR is having. But it is rather interesting to look at to what kind of effect the SCR and DOC is having on the emissions when it is not fully operational. And this occurs, in low load situations when the temperature of the exhaust is not at the peak efficiency for the SCR. And previously we did show that the vessel does spend a large amount of time in these low load conditions. So it's rather interesting to look at. And then as a summary, both those vessels did reach their certification level for NOx emissions, and then also both vessels showed the bimodal kind of distribution where they spent a large amount of time below 30% load, but then also a decent chunk of time above 80% load, and then not much in between. And I believe that concludes my presentation. Thank you.
Okay, thank you, Chaz. Any questions from the audience? I'm just curious because I'm not familiar with the non-roads. Are the vessels emissions comparable to the light duty automobiles on the road?
I'm not too sure about that. I don't know if I can say. I think so.
Okay, any other questions? Or you can, if you are still typing, you can do so. So if we have time after third presenters, we can maybe get some extra questions answered. Okay, so thank you, Chance. Let's move to our next presenter. Is Jason Braun. So Jason is a principal air quality planner in the transportation department in the North Central Texas Council of the Government. Jason oversees air quality programs and strategies targeting on-road vehicles producing excessive emissions to get them compliant with emission standards. He has been with NCT COG since 2006, and prior to NCT COG, Jason worked in the stack emissions testing industry. So Jason, whenever you're ready.
Okay, thank you. Haobing, can you hear me?
Yes, I can hear you.
Thank you, everyone who's joined us for this session. Appreciate this opportunity to present our study here. I work with, as you mentioned, the North Central Texas Council of Governments. I'm a principal air quality planner within our transportation department at our agency. And today I'm presenting some highlights on the heavy-duty vehicle emissions impact study. We did this in coordination with the Texas A&M Transportation Institute, TTI, and it was set up to study and investigate how oversized and overweight heavy-duty diesel vehicles have their emissions that impact air quality in our Dallas-Fort Worth non-attainment area. Now, we had the pleasure to work with TTI's Environment and Air Quality Division. They did a bulk of the work and really wanted to provide those that represented TTI. It was Yolanda Prozai, Reza Farzana, Jeremy Johnson, Adam Mayer, and Madhu Venugopal. So really enjoyed working with them. And this occurred over a 2-year period. The project itself, some of the data that was analyzed was some different time period, but we wrapped this up about the spring of 2020 with the final report. And as the study progressed, we actually had a chance to update and talk about some of our data and findings with several Texas state agencies, the Texas Department of Public Safety, and the Texas Department of Transportation. So we wanted to make sure that they were aware of what was going on and findings that were happening. And then we had the opportunity to also provide the final study through other stakeholders, EPA representatives. So before I get into the study, let me just quickly mention the Dallas-Fort Worth region. It has 10 counties. So this is the north central Texas area. We have 10 counties that are designated non-attainment and do not meet federal standards for ground level ozone. Another factor to take into place in consideration is the large ratio of the VOC, the volatile organic compounds, to the NOx means that our North Central Texas region is NOx limited. So it results in ozone formation being much more sensitive to changes in NOx than VOC. So this fact really leads us to address ozone by focusing on NOx reduction in our particular area. Now, in this graph, this slide, I'm sorry, if you'll notice the left side, the pie chart, it shows the NOx emission sources in our Dallas-Fort Worth non-attainment area. The various trucks on the road. So the portion of the overall emissions here, you'll notice the on-road mobile sector, that equates to about approximately 38%. So again, this is the more of the NOx emissions centered from our mobile transportation sources. And then if we break that out a little to the right there, kind of in the center of the slide, it breaks out light duty, heavy duty, medium duty. The heavy duty vehicles, kind of that gray color there, they're a major contributor, equating to about 48% versus the light and medium duty that combine at about 52%. So our air quality initiatives in our region, as I mentioned, with the NOx limitation, the fact that we also want to focus on not only light duty cars and trucks, but heavy duty diesel vehicles in our region. The image on the right side of the slide just shows speed curves for analysis year 2020 from the MOVES model emissions factors. And a key relationship here is between the NOx and VOC with those colored lines. And so the blue color being the NOx vehicles, you can really see that the heavy duty NOx stands out well above and shows a sharp increase as at those lower speeds. So again, just to meet the federal ozone standard, it's necessary that for our area, we're moving to address major contributing factors, and that's where our focus is to work on air quality programs, make policy recommendations, participate in partnerships and collaborations, and also support our other stakeholders that are also doing their own emission reducing activities. Now for the study, one of the main goals of the study was to characterize and estimate emissions and the impacts of oversize over
Jason, your words are kind of in and out bumping in my side.
Yes, I've also lost him on my end too.
Hello, can you hear me?
Yeah, I can hear you now.
Okay, I'm sorry. I didn't see anything. Okay.
Mm-hmm.
So I should be on slide 3. And so essentially, what I'll just point out, I guess, is that for the purposes of this study, overweight vehicles equated to weights that were over 80,000 pounds or above, and those require a permit to operate. And so I'm highlighting in this presentation just some key points regarding the overweight vehicles that were studied. We certainly have more information on oversize characteristics in our full study. And so just quickly to go into our testing design, one of the main tasks and what I kind of wanted to focus on for this presentation was just the tailpipe data collection aspect of it. So that there was tailpipe data collection through using the Portable Emissions Measuring System, or PEMS, for both gaseous and particulate matter emissions. The testing was done on 3 heavy-duty diesel trucks covering different model years. So we had a model year 2005, model year 2009, which those trucks actually had, they were, without some of the key emissions technology components, emissions controls, particularly the SCR technology. And then we had a 2014. Now, each of the vehicles was outfitted with the PEMS device and then driven on a route that covered various high speeds, so up to 70 miles per hour on a highway route, and low speeds, so from about anywhere from 0 to 45 miles per hour, to represent arterial road driving conditions. And each vehicle was tested under different weight loads. So this right here just gives you an idea of how those were set up. So the slide shows the trucks with various weight loads on the trailers to bring the vehicles to the upper left corner. A is the normal load. So it resulted in approximately about 55,000 pounds. The one over towards the right, kind of top right, B, that was a medium load, or what they said as the legal limit. So it was approximately 80,000 pounds. And then the overweight load, So kind of just as I mentioned, there was a lot that was, to dive into with the study. And so I'm just providing some of the results based on the PIMS analysis. But the next couple of slides will show some key results from the emissions that were collected on the test vehicles. So on this particular one, the table at the top of the slide, it shows NOx emissions of the 2 trucks that were model year 2005 and 2009. And again, these were the vehicles, they did not have SCR technology. And as they were driven around at the higher speeds on freeway condition and lower speeds to represent, a local street or arterial. And so as what's shown here is that for both routes, when we're looking at the freeway kind of in the middle and arterials are broken out kind of to the right of the table, an increase in load weight equates to higher NOx emissions, with more than double the emissions rate for the overweight vehicle. And then also a key consideration is that older vehicles have higher emissions due to deterioration of the engine. Now here, kind of just focused on the model year 2014. So this was the SCR equipped truck. And what we're seeing here is there is a difference when you look between the arterial and freeway route. The lower speed arterial, it keeps with the same trend as seen with the other trucks. So the NOx increased with weight increase. However, for the model year 2014, it showed that for higher speed and acceleration combinations, the NOx emissions actually decreased as weight increases. So generally speaking, for highway routes, the lower weight loads have an exhaust temperature that is below the SCR's effective temperature range, therefore seeing increased NOx emissions. And just to kind of show that a different way here, we can see the impact of the exhaust temperatures. They were examined by extracting the SCR temperature data that corresponded to the as I talked about, the portable activity measurement device. So when there was actually gathering activity of some of the vehicles, the graph at the top shows the profile of the exhaust temperature and the recorded instantaneous NOx emission flow. So so basically what we're seeing here is that once the exhaust temperature is over 200 degrees Celsius, or kind of that middle section of the graph, the NOx readings are substantially lower than when the exhaust temperature is below 200 degrees Celsius. So when you see kind of the beginning and the end time sequence there of the graph. And further examination of the speed profile kind of reveals 2 trends. First, the exhaust temperatures are higher than 200 degrees Celsius when the vehicle is traveling at highway speeds. And second, there's changes of exhaust temperatures are gradual. So as a result, a low speed or idling event occurring immediately after a high speed event may still have an exhaust temperature higher than 200 for a period of time, a short period of time. So just quickly to summarize, for our particular perspective, there are things that we want to take into consideration. Based on the information, vehicle weight is an important parameter that influences emissions, as well as the condition of the vehicle, emission control technology. There's obviously many things here involved when you're looking at particular trucks on the road. But we did see an increase in weight can result in increased emissions and fuel consumption. And there is limited existing research on emissions impacts of vehicles when you're looking at these kind of overweight, oversized. And so we hoped that to better understand characteristics and their impacts through this study. But one thing I did want to point out is we kind of consider, what are kind of the next steps. I think we may have an opportunity to think about a permit fee or requirement revisions, something that may incentivize using, newer trucks. So potentially a 2009 and older truck may not be the best, emitting lower emissions compared to 2010 and newer trucks. So maybe we could do some, make some emphasis on those newer trucks, having these permitted loads. They may offer improved air quality. And then for our particular region, we continue to help to identify and promote funding opportunities to our freight industry, heavy-duty fleets, and drivers for incentivizing to replace higher-emitting trucks and equipment, and continue our efforts as we play a role in the region's transportation planning. We want to help to ensure that we're using this information to enhance modeling, so that we don't underestimate emissions coming from different sources. So a lot of things to consider here. And I'll close with my contact information. I appreciate the opportunity to present to you today. And then there are links here to our final report and additional appendices. Thank you.
Thank you, Jason. Any questions from the audience? We have about 8 minutes left for this session. Or any other questions for the other presenters? I think we got some questions from for Phil, but I think it seems like he already logged off since he has a travel plan. Okay, so we got one question from Victoria. The lower NOx emissions at higher weights and the speeds were in newer engines.
Okay. Yes, I think if I just go back to so this particular one, again, we realize that the sample size here is not very large. So, but in looking at what came out of the actual tailpipe emissions results, it did show that, okay, as the vehicle was traveling under the overweight load and on freeways, it actually performed better. So it actually had a lower NOx emission.
And Jason, if you can go to page 8, when you show, the exhaust temperature, I'm just trying to figure out the causality relationship between those lines. Why do you show the exhaust temperature here? Or do you think that the emissions, the reason for the higher emissions has something to do with the temperature?
Right.
Or
yes.
the top two lines are
exactly.
Yeah.
So we're exactly. Yeah. So yeah, there's definitely I think this correlation or what you can see there is as the temperature gets, it's kind of showing that there is this maybe optimal condition for the temperature to reach in order to really knocked out and reduce the NOx. So what we're seeing here is that as the temperature rises, the NOx really substantially lowers, and that's equating to let's see here. I was trying to go back to so we've got the exhaust temperature. So it's exhaust temperature, and then it's the instantaneous NOx emission mass, which is shown in the milligrams per second. of the overweight scenario. So this is the overweight 2014. So yes, if you look in there in the middle of that top graph, you'll see there seems to be a role with the temperature really knocking out the NOx, is that it seems to, you know, reach that 200 or higher.
All right, thank you. Did I miss other questions? I think no. Any other questions? Yeah, okay, good. Okay, so Daisy's question has been answered by Chance. Thank you for that. If no further questions, thank you, Chance, Jason, and Phil for the great presentations today. And I also want to thank all the audience for joining us today. And I hope to meet you guys virtually in the other sessions. And have a good rest of your day. Bye-bye.